looks very calm, the shuttle's moving very slowly, and it just slowly approaches, and eventually the two connect. It's anything but benign.
All of this work that's happening, whether it's docking, whether it's doing special things with the arm.
It involves thousands and thousands of bits of data flowing back and forth between the space station, the space shuttle, and the ground. It involves hundreds of voice lines with people communicating, making sure that all of those systems are working right. That whole sequence happens because of the careful design that has gone into the communication network.
We're the ones that provide that link to communicate and distribute that data between the orbiting satellites, the space station, and the scientists on the ground that use the information and data that are gathered by the satellites.
So when it comes to how NASA's communications networks got started, it all began during the times when the first astronauts were going to be flying and when the first satellites were going to be launched. They needed a way to get all that information from the satellites down to the Earth. And so the idea was, why don't we put antennas all around the globe so that no matter where you were in your orbit, you could always send data down and get it successfully back to Earth.
In order to maximize the amount of data that we could collect, we had to have them in the right positions.
So you had to have one in all different countries. And when you think about that, there could be some countries where you might not be welcome. There could be some countries where governments are changing and it might not always be a safe environment. So back in the early days, NASA had dozens of sites around the world. And the hub for that system was here at Goddard.
So Goddard has been the home of space communications for a long time, for the existence, almost the entire existence of NASA. What we're getting is approximately 15 to 20% of the available contact time for any given orbiting satellite.
So you can imagine if you're an astronaut, there's a big difference to you whether you're in contact with the ground 15% of the time or close to 100% of the time in terms of if something goes wrong and you're looking for help, or you're looking to send data to the ground and you want somebody to look at it and tell you what to do next.
We said, hey, there's got to be a better way, and that's when the concept of a space-based relay system came into being.
0 and liftoff. Liftoff of the orbiter Challenger.
And so starting in 1983, as we started to deploy a fleet of these tracking and data relay satellites, that gave us the capability to take data from low orbits, shoot it up to these geosynchronous satellites. You think about that, that's like an antenna on the ground. It's the same idea. You now have an antenna up in space that can communicate back and forth to the Earth. White Sands, New Mexico is the location where we bring that data down to Earth. It's an offshoot of Goddard Space Flight Center. And so there are landlines and all kinds of satellites that are used to send that data around.
If you're an astronaut, then what TDRS does is very important because it gives you full-time contact, not just voice, but video with the ground station, so you can talk to controllers pretty much all the time.
So when the tracking data relay satellite system came online, the goal was to get rid of most of those ground assets. But it quickly turned out that for a lot of space science missions or Earth science missions, it's not the right answer is to have this big satellite up in the sky.
For Earth science users, they typically are in polar orbits where they want to cover as much of the surface of the Earth as possible. So something in polar orbit is going to go by the North and South Pole, such that you can collect all your science data through your orbit and hold on to it, and there's not a rush to get the data down. And you can collect a whole bunch of data, and 45 minutes later, an hour later, 3 hours later, and you come over a ground station and you just send it all down to the ground in one pass. Putting ground stations in places like Alaska or McMurdo in Antarctica or things near the poles then allows that ground station to see the satellite many more times.
Right now, when it comes to satellites that communicate directly to the ground, NASA buys about half of the services we use every year from commercial providers. And then we have stations that we own ourselves that provide about the other half of that capability. Between the Near Earth network, which is the ground-based antennas, and the space network, the space-based antennas, we support about 100 missions.
If something is out there and you can't communicate with it, then it doesn't matter if all of the science instruments are working, if Hubble is taking the most incredible pictures. it doesn't matter.
It's pretty impressive, the reliability and availability of the system, and to know that you've got, you know, a rock solid communications system supporting you and supporting your satellite is very, very, very comforting thing from a user perspective.
In the future, missions will be collecting more and more information to better understand our Earth and the universe. And we have found that the best and most efficient way to communicate those large amounts of data is through beams of light or laser communication, which we're currently developing, building, and testing for an upcoming mission.
When it comes to the Exploration and Space Communications Group, the bottom line for us is advanced communications for mission success.